In this video, we are going to take a look at the concept of entropy, which essentially forms the foundation of all machine learning. All the modern deep learning concepts that you might have seen, they are essentially trying to reduce entropy. So if you understand entropy, almost all the state-of-the-art models, doesn't matter whether they come out now or 5 years from now, you'll be able to understand them. So let's go ahead and ask a very simple question. This is going to relate to the expected values concept we studied in the previous lecture. But let's start off with a very simple question. So let's say you flip a coin and I tell you beforehand that this coin only lands on its head. Before even flipping the coin, I've told you this. It can only come up heads or heads. So it's only heads. So the question we're trying to ask is, how much information do you get out of it when you do flip it? So it's a very complicated question. What do you mean by information, right? So we're going to define what information is, but at the moment, we know that we don't get any information out of it. Even before the flip, I told you that it's going to be heads. So if you do flip it and it does come up heads, you found out no new information. So no new information we are going to define as zero information, and the units that we are going to have for information is bits. So think of it this way. You decide to measure a distance between two cities and you say that the distance is 1,000. And what is the unit for distance? It's kilometers. So 1,000 kilometers or miles. So here we are taking the concept of information and we are defining bits as its units. And because we did not get any information out of it, we have 0 bits. Okay, we're going to define what a bit is in a while. And 0 we already know because nothing is 0. Okay. Now we will define a bit of information, a single bit of information as, and this is going to make sense in a little while. The definition of a bit is going to be how many yes/no questions you need to ask to determine the outcome of an experiment. So for this experiment particularly, you did not need to ask any questions. Before me telling you anything, you already knew that it was going to come up heads. Okay. How about if we have a probability of heads equal to 0.5? So that means that it can come up heads or tails. Now here, when I flip the coin and hide that coin from you, you need to ask me yes or no questions. And the yes or no question that you might ask is, was it heads? I tell you yes. So you know that it was heads. To arrive at the outcome or to determine the outcome, you need to ask me only one question. And that is why we say that the information in this experiment or this coin is one bit of information. Right? Hope that's making sense. I'm going to go slow so that you understand the whole of this concept because we are going to use this in a case study in the next video. Now, let's do 3 coin flips. So that can be 3 bits. Why? Because you need to ask me first, was the first flip heads? I say yes. You go here. You say, was the second flip heads? I say yes. You go here. You say, was the third flip heads? I say no. You go here and you get the outcome after 3 questions. So that's 3 bits of information. Okay, hope that makes sense. So remember this definition. This is not an academic exercise. This is extremely important. This is going to differentiate you from average machine learning and data science experts. Okay, so that is how we define information and bits. What about the English alphabet? What if I tell you pick a random letter from A to Z? Now, which question can you ask? If you follow this naive approach, you can ask me, was it an A? I say no. You say, was it a B? I say no. Was it a C? No. So you ask 26 questions and you arrive at the final answer. A minor difference is that you don't have to actually ask me about Z. So if on Y I said no, then you already know that it's not the other 25, so it has to be Z. Okay. So you actually only need to ask 25 questions, but that's not important. What's important is that we have another way of asking these questions, which is going to reduce this number by a lot. Let's see how that is. So pause and think about what questions can you ask so that you can arrive at, let's say, D very quickly. Okay. So here's the question that I'm going to ask. I'm going to take the whole thing, the whole English alphabet. I'm going to split it in 2 and I'm going to ask you, is it M or before M? Remember, this is a yes/no question, so it's valid. Is it before or on M? If you say yes, I can get rid of all of these. And these are my possibilities now. Then I can ask you, is it on or before G? If you say yes, I can discard these and I'm left with only these. And so on, I can keep going. So the number of questions that I have to ask to arrive at any letter is going to be log to the base 2 of 26. Why is that? Let me try to explain that to you. If you don't remember logs, it's fine. I'm going to cover this very briefly over here, but it's not really important if you can trust me on this, that it's going to be log to the base 2. But it's good exercise to practice your mind about this. So you can say, is it less than n? If yes, you go over here. Is it less than g? So you keep going. Is it less than d? You say yes, I go here. Is it less than b? You say yes, and now I know that it is a. So here it's going to be less than d, then it's going to be less than b, and we're done. Okay, so this is 1, 2, 3, 4. So what this is saying is you need to ask only 4 questions to get to a. Similarly, if you do for q and r and s and all of those, you will figure out that because these are odd numbers and even numbers, a lot of that is going on. So on average, you are going to get 4.7, right? So 4.7 on average, you are going to get those questions. Why do we have this log over here? We need the number of these questions, 1, 2, 3, and 4. So log, if you don't remember, log to the base 2 of x means what number do you raise 2 to arrive at x. So you need this number, right? So 2 to the 4 is equal to 16, okay? And 2 to the 5 is equal to 32. So 26 is somewhere in the middle over here, 4.7. So that is why we have this idea. So log is really important here, and it's log to the base 2 because of binary, yes, no, 0, 1, all of that. It's not important. If you don't understand that, that's fine. You just need to remember that we have log to the base 2 of 26 number of questions on average for the English alphabet. You can do it for another language as well. So this is the number of questions we have. Let's consider just A, B, C, D and try to explain this a little bit further. So this is the whole concept. We are going to drill this down further and try to understand this in detail. So let's just consider A, B, C, D for the minute. So we have a sequence A, B, B, C, C, D, D. If I pick a letter from any of these, how many yes, no questions do you need to ask before you arrive at the outcome, right? So you can ask, is it an A? Then you can ask, is it a B? Then you can ask, is it a C? So first, let's consider what the probability of A is. So it's 1 over 4. So the first question that you ask is, was the outcome A or B? It's a yes, no question. It's valid. So if the answer is yes, you go over here and you can ask, was it an A? If that was a yes, then the outcome was A. If that was a no, the answer was B. Similarly for C and D. Okay. So you can arrive at your answer in just 2 questions. Make sense? So the number of questions to find out if it's an A is equal to 2. And the probability of A is 1 over 4. So we're done with A. We do the same thing for B. So the probability of B is 1 over 4. And the number of questions we need to ask is again 2. So 2. Same for C and same for D. We take the average of all these 2's and we get the value out at 2. Let's try to formalize this a little bit. Okay. So total expected value of number of questions is, you take the number of questions for this letter, multiply by that the probability of this letter. So you recall the expected values. These are the value of the random variable multiplied by the probability. So that's exactly what we're doing over here. So this is the expected value of the number of questions. How many questions do you expect to ask for A multiplied by its probability, added with the number of questions you want to ask for B multiplied by that probability, and so on. So that is the expected number of questions that you have to ask for each letter. Okay. So that's going to be this calculation over here, which is essentially 2. And you will notice that this is log to the base 2 of 4. So if you raise 2 to the power 2, you get 4. So 2 questions over here. Okay. So our formula does fit over here. Now let's go ahead and change the sequence a little bit. A, B, B, and C, D. If you do the same thing over here, this is not going to make sense because we can do much better than this. Try to do this on your own and calculate the expected values for this sequence. A, B, B, and C, D. See what comes out. We are going to ask separate questions. We are going to ask, was it an A? If you say yes, then we have already arrived at the outcome. If you say no, then I can ask you, was it a B? If you say yes, I arrive at the answer. If you say no, then I ask, was it a C? In case of yes, it's a C. In case of no, it's a D. Okay. So let's calculate the expected number of questions for this now. So the probability of A is 4 over 8. For this, because 4 divided by total 8 is equal to 1 over 2. The number of questions to find out if it's an A is just 1. This guy over here. Okay. So we arrange this very particularly in a very specific pattern. So the expected number of questions for this whole thing is this guy for A, 1 over 4 into 2, because we need 2 questions for B, we need 3 questions for C and 3 questions for D, and for each of these the probability is 1 over 8. Okay. So when we do that, we get average number of questions at 1.75, and this is of utmost importance over here. For this sequence A, B, B, C, D, the best we can do is 1.75, and for this sequence the best we can do is 2. Okay. There are theorems saying that this really is the best you can do, but we don't want to go into that. What's important over here is to note that this guy, AA, BB, CC, DD, they have a higher entropy, because that is how we define entropy. The number of questions on average that you have to ask to arrive at the outcome. So this has a higher value of 2 and this has a lower value of 1.75. Now think about it this way. If you were trying to train a machine to differentiate between two things, you show it an animal and ask it which animal is it. You want the machine to be in a state so that it only needs a little bit of information. It needs to ask very few questions to arrive at the outcome. That is where the whole concept of machine learning comes in. Try to focus on this. I'll repeat it again. If you show an image to a machine, you want the image to be in a state so that the machine can arrive at the correct answer by asking the fewest number of questions on average. That means the machine will produce the answer quickest. So what we want is, we want the machine to be in a lower entropy state, or our data to be in a lower entropy state. So this, we are going to say that this is all, they are all jumbled up. So they are called unordered. And these things are in a slightly better order because there are a lot of A's over here. So we are going to call them ordered. Imagine that if there was a sequence, we managed to get all the A's in place, right? So if they are all the A's, then you don't need to ask any questions. You already know that they are A's. So the entropy is exactly 0. That is the best case scenario when you already know the answer. Okay. So if you put the data in some sort of a situation where the machine looking at the image immediately knows without doing any work that that image is of a dog, then you've done a really good job. Okay. And this is exactly what we're going to do in the next video, but let's finish off this theory part first. Okay. So points to note, you have to ask more questions to gain knowledge if the entropy is higher, right? So gain knowledge is essentially arriving at the outcome. If a machine is trying to learn something, we want to minimize the entropy so that it learns with fewer questions. When transmitting information, we want to minimize entropy. So the number of questions asked. So this is kind of optional. So let's put that in brackets. But if you know what Hoffman coding is, maybe you've studied it somewhere. So Hoffman coding is essentially this exact thing. Okay. It's studied in basic computer science courses. Okay. So the total expected value, let's finish this off. Total expected values for the number of questions is the number of questions for this letter. So this is the information multiplied by the probability of this letter. So how do you arrive at the number of questions? So looking at this, we will see that the higher the probability is, if A is very frequent, so A is very frequent over here, we are going to reduce the number of questions it has. Okay. If it is very infrequent, we are going to increase, we are going to arrange it in a way that we have to ask more questions for it. But that makes sense. Something that is very frequent, we want to arrive at it quickly so that our average time goes down. If something occurs only very rarely and we have to ask a lot of questions for that, then it's fine. Okay. Hope that makes sense. So what we say is that the number of questions for A is going to be 1, which is minus log of 0.5. Okay. So where did this come from? This comes from some theories of logs and data structures. We don't want to go into that. Let's take a look at the values for B, C, and D, and hopefully it will make sense. So for B, you need to ask 1 and 2 questions. So that is minus log 2 of 0.25. So the lower the probability, the higher the number. Okay. So think of it this way. This maths just lets us arrive at this. Okay. We're going to skip over some of the proofs here. They're not really important. So the lower the probability, the higher the number of questions. Okay. So once you know this, the number of questions is this guy over here. So we can go ahead and replace this Q with this minus log into probability. Okay. So this is minus log to the base 2, which is sometimes written as LG, the probability of X. Okay. So this is all of these three. Okay. So let's go ahead and put this value minus log of px into this equation over here, and we'll see that the summation of L, that is over here, this probability as before goes over here, this q gets replaced with this, okay, and we take this negative sign over here and move it outside the equation. So this is our equation for entropy. And because this guy over here, you will recall that this was the expected number of questions. This was the expected number of questions, and questions are information, the amount of information that we defined earlier. So entropy is the expected information that you get out of it. For instance, let's finish this off with a simple coin flip again. So the probability affecting entropy of a coin flip. So if your probability of getting a heads is exactly 0, then you don't get any information out of it. So your entropy is exactly 0 because you already know that it's going to be a head. Similarly, for this other end, if you know that it's never going to be a heads, then again, you don't get information after actually doing the flip. It's going to be tails. We already know that. If the probability is 0.5 for this coin flip, if the probability is 0.5, then there is maximum uncertainty. It's perfectly disordered. For this coin flip, the maximum entropy that we can get is 1.0. Okay, because you really don't know what is going to come out, right? So let's put our probability of 0.1 into our formula. So this is 0.1 probability into log to the base 2 of probability, 0.9, which is the probability of tails, multiplied by log to the base 2 of probability of tails, which is this guy over here. If you do the calculation, do the minus, you get 0.46. So if your coin has the probability that the outcome, random variable x, is going to take on the value h is equal to 0.1, then we can say that the entropy of x is equal to 0.46, right? So this is the relationship between entropy and probability for a coin flip, a single coin flip, okay? Some people mistake this to think that the maximum value of entropy is 1.0. The maximum value of entropy is not 1.0. It can be more than that. But for a single coin flip, the maximum possible value of a probability is 1.0. We can have an entropy larger than 1, as we saw over here, right? So let's go back and recall what we've done in this lecture. We started off with trying to define the concept of information, and we defined information as how many yes no questions you need to ask to determine the outcome of an experiment. That we defined as information, and the number of questions had a unit of bits. Okay. We then went ahead and tried to define the expected number of questions we need to ask for different sequences or different collections of objects. So here we have an object in which everything is jumbled up, so it's unordered. We say it has a higher entropy. If we have slightly more arranged objects, slightly more ordered objects, they have a little bit of order in them, they are arranged neatly, they have lower entropy. So what we want to do is somehow take the mess of the whole world that we are trying to learn or trying to get the machine to learn, and we are trying to lower the entropy of the different groups that we create. This is the whole formula that we need. We are going to take this very simple formula and we are going to turn this into one of the most powerful machine learning algorithms that is in use even today.